Every atom in your body is older than the earth, older than the sun, older than every mountain, ocean, and living thing that has ever existed. The iron in your blood was forged inside stars that died billions of years ago. The carbon in your cells was scattered across the galaxy before our solar system even existed. You are not a person carrying ancient matter. You are ancient matter that became aware of itself. But what happens when that awareness ends? Can it end? In 1997, a physicist began exploring a question that sounded more like philosophy than science. If the equations of quantum mechanics are taken completely literally, what happens to a conscious observer facing an event that should be fatal? The answer led somewhere deeply strange. Quantum mechanics is the most successful scientific theory ever created. Every laser, computer chip, and MRI machine exists because its equations describe reality with extraordinary precision. And yet, those same equations contain a possibility that some physicists have spent decades arguing over. What if every possible outcome of every quantum event actually happens? What if reality continuously branches into countless versions of itself? And if it does, what happens to you? Does consciousness exist in only one branch? Could some version of you continue wherever survival remains possible? Could the permanent ending of conscious experience be incompatible with the way quantum mechanics describes reality? These questions are not coming from religion. They are not coming from spirituality. They emerge directly from one of the most successful mathematical frameworks ever developed. And the deeper physicists followed that logic, the stranger the implications became. A like, a subscribe, whatever feels right. It all helps this channel reach more people who love falling asleep to the sound of the universe. Now, let's begin. Long before quantum mechanics became associated with mystery, it began as a practical problem. Physicists were studying ordinary objects, heated metal, glowing furnaces, and the colors emitted by hot matter. The equations of classical physics, which had successfully described planets, falling apples, and moving machines, suddenly stopped working. The predictions did not match reality. Something deep inside nature was behaving according to rules no one yet understood. In 1900, a German physicist named Max Planck proposed a solution that even he considered temporary. Energy, he suggested, could not be exchanged in an endless smooth flow. Instead, it arrived in tiny discrete packets. He called these packets quanta, a word meaning a fixed quantity. What began as a mathematical shortcut soon became something much larger. Nature itself appeared to be granular at its foundations. 5 years later, Albert Einstein pushed the idea further, studying a phenomenon called the photoelectric effect, where light ejects electrons from metal surfaces. He concluded that light behaved as individual packets rather than a continuous wave. These packets became known as photons. The work earned him the Nobel Prize and helped establish a new picture of reality, one in which matter and energy behaved in unexpectedly fragmented ways. Over the following decades, some of the greatest physicists in history assembled the framework that still governs modern quantum theory. Niels Bohr explored atomic structure. Werner Heisenberg developed new mathematical tools. Erwin Schrödinger created an equation describing how quantum systems evolve through time. Paul Dirac unified key elements into a remarkably elegant form. By the early 1930s, the foundation was largely complete, but the theory revealed a universe unlike anything common experience prepares us for. At the scale of atoms and particles, objects do not possess definite properties in the familiar sense. Before measurement, a particle can exist in what physicists call a superposition, a combination of multiple possible states existing simultaneously within the mathematics. Position, motion, and other properties remain spread across possibilities rather than fixed to a single outcome. Schrödinger's equation describes this evolution with extraordinary precision. It is one of the most successful equations ever written, yet it never tells us exactly where a particle is. Instead, it provides probabilities, mathematical forecasts describing where a particle may be found when observation occurs. This probabilistic nature is not a flaw in our instruments. It is built directly into reality itself. Heisenberg's uncertainty principle demonstrated that certain pairs of properties, such as position and momentum, cannot both possess perfectly defined values at the same time. The limitation belongs to nature, not to us, and this is the ground beneath everything that follows. Every discussion of consciousness, identity, survival, or death rests upon these equations. The strangeness is not an interpretation layered on top of quantum mechanics. It emerges naturally from the mathematics that already powers the transistors, lasers, satellites, and computers surrounding us every day. A detector clicks inside a laboratory, a screen flashes, a number appears on an instrument. We tend to think the event is complete. A particle had a property, the machine revealed it, and reality carried on exactly as expected. But quantum mechanics tells a stranger story. Before any measurement occurs, the mathematical description of a particle is not a record of ignorance. It is not a placeholder for missing information. According to Schrödinger's equation, the particle genuinely exists in a superposition, a state containing multiple possible outcomes at the same time. Different positions, different energies, different futures, all remain woven together within the mathematics. Then something happens. When an observation is made, only one result appears. The particle is found here rather than there. One outcome becomes real in experience. The others vanish from view. Every experiment ever performed agrees on this basic pattern. We calculate many possibilities. We observe one result. The difficulty is that the equation itself never describes the transition. Schrödinger's equation evolves smoothly through time. It never contains a step where possibilities suddenly become a single reality. Physicists have been wrestling with this gap since the 1920s. The puzzle became known as the measurement problem, and despite a century of effort, no universally accepted solution exists. One of the earliest responses came from Niels Bohr and Werner Heisenberg. Their approach, later called the Copenhagen interpretation, proposed that the wave function collapses during measurement. A wave function is the mathematical object containing all possible outcomes. Before observation, multiple possibilities coexist. After observation, only one remains. The idea works remarkably well in practice, yet it leaves uncomfortable questions behind. What exactly counts as a measurement? Does a detector qualify? Does a camera? Does a grain of dust interacting with a photon count? Where does the quantum world end and the familiar world begin? The interpretation provides useful rules, but it offers no precise boundary. In 1932, mathematician and physicist John von Neumann examined the problem more deeply. He followed the chain of events step by step. A particle interacts with a detector. The detector affects electronic circuits. The circuits influence a display. The display reaches an observer's eyes. Signals travel into the brain. Where, along this chain, does collapse occur? Von Neumann found no obvious location. Every component could itself be treated as a quantum system. The problem simply moved further along the chain without disappearing. This led some researchers toward a startling possibility. Perhaps consciousness itself plays a role. Perhaps reality remains undecided until a conscious observer becomes aware of the result. This proposal became known as the von Neumann-Wegener interpretation after von Neumann and physicist Eugene Wigner. It remains controversial, but it was developed by respected scientists working within the mathematics, not outside it. Today, the debate continues. Different interpretations preserve the same experimental predictions while offering profoundly different pictures of reality. The equations remain unchanged, their meaning does not, and the meaning matters. Some scientific ideas arrive gradually, gathering support over decades before anyone notices their significance. Others arrive all at once, appearing so strange that even experts struggle to take them seriously. In the spring of 1957, a young graduate student at Princeton University placed one such idea onto the desk of his doctoral committee. His name was Hugh Everett III. Everett was only 27 years old, yet he was willing to challenge one of the central assumptions of modern physics. Most physicists accepted that quantum possibilities, somehow reduced to a single outcome when measurements occurred. The details remained uncertain, but the collapse of the wave function had become part of the standard picture. Everett asked a deceptively simple question: what if the collapse never happens? Instead of modifying Schrodinger's equation or adding extra rules, Everett proposed trusting the mathematics completely. The equation had survived every experimental test. It evolved quantum systems smoothly and continuously. If the equation never contained a collapse, perhaps nature never contained one either. The consequences were astonishing. Imagine a quantum event with two possible outcomes. A radioactive atom either decays or it does not. Traditional interpretations require one result to become real while the other disappears. Everett suggested something different. Both outcomes occur. Reality itself divides into separate branches, each containing one outcome. No possibility is eliminated. Every allowed result becomes part of existence. Everett called this framework the relative state formulation. The name never captured public imagination. Years later, physicist Bryce DeWitt began referring to it as the many worlds interpretation. The new label spread quickly and became one of the most recognizable ideas in modern theoretical physics. Within this framework, randomness largely disappears. What appears random from your perspective is simply uncertainty about which branch you occupy. The underlying wave function continues evolving according to the same mathematical rules at all times. No special moment of collapse interrupts the process. Branching becomes universal. A photon taking one path rather than another creates new branches. A radioactive nucleus undergoing decay creates new branches. Every microscopic event capable of producing multiple outcomes contributes to an ever growing structure of realities. The number of branches becomes so vast that ordinary language struggles to describe it. It is not merely enormous, it may be effectively beyond counting. Yet Everett received little recognition during his lifetime. Many colleagues considered the proposal too extravagant. Others viewed it as philosophy rather than physics. Frustrated by the academic response, Everett eventually left university research and entered defense work. He spent much of his career outside mainstream theoretical physics and died in 1982 at the age of 51. But ideas sometimes travel farther than their creators. As decades passed, new generations of physicists revisited Everett's work. They discovered that his interpretation removed several conceptual difficulties without altering a single successful equation. Surveys conducted at major conferences began revealing growing support. By the early 21st century, many worlds consistently ranked among the most favored interpretations of quantum mechanics, transforming a once dismissed thesis into one of the most influential ideas in modern physics. Consider a single moment so ordinary that it barely registers. A photon enters your eye. A neuron responds. A microscopic event unfolds somewhere inside the circuitry of your brain. Nothing seems remarkable. You continue listening. The night continues around you. Yet within the many worlds framework, events like these are where reality becomes astonishingly crowded. The idea is often misunderstood as a poetic image or a science fiction metaphor. It is neither. If Hugh Everett's interpretation is correct, branching is a literal consequence of quantum mechanics. Whenever a quantum event allows multiple possible outcomes, every outcome occurs. Reality does not choose between them, it contains them all. This means that a branching event is not a fork where one path survives and another disappears. It is a divergence where multiple futures continue simultaneously. Each outcome exists within its own branch of reality, evolving independently from that point onward. Crucially, the observer branches as well. Suppose a quantum event produces two possible results. In one branch, you observe the first outcome. In another, you observe the second. Both versions of you are equally real. Neither possesses any special status. There is no privileged timeline hidden beneath the others. No master version remains behind, while copies split away. The branching extends upward through every level of physical organization. It begins with quantum systems. Then chemistry reflects those outcomes. Biology inherits them. Neural activity incorporates them. Information spreads outward through cells, organs, bodies, and environments. A microscopic divergence becomes a macroscopic history. This process is happening constantly. Photons scatter from surfaces, molecules collide, electrons transition between energy levels, radioactive nuclei decay or remain stable. Every event capable of multiple quantum outcomes contributes to an ever growing structure of branches extending through reality. But from your perspective, none of this feels unusual. You never sense a division occurring. No alarm sounds. No boundary appears. Conscious experience remains seamless. Each version of you remembers the same past and carries the same identity up to the instant branching occurs. The continuity feels perfect because, from within a branch, it is perfect. This creates one of the most unsettling consequences of Everett's framework. The versions of you inhabiting other branches are not strangers. They are not duplicates manufactured afterward. They possess your memories, your history, your relationships, and your awareness. Until the branching event, they were literally the same observer. Then their experiences diverge. One version sees one outcome, another sees a different outcome. Both continue forward, believing themselves to be the natural continuation of the life that came before. In this picture, every future permitted by quantum mechanics is realized somewhere, not imagined, not merely possible, real. What you experience is only one thread moving through that immense structure. Other threads continue beyond your awareness, carrying other versions of your story into different circumstances, different outcomes, and different destinies. The remarkable question is what happens when one of those threads reaches a point where continuation seems impossible. In 1997, a physicist at the Massachusetts Institute of Technology took an already controversial idea and followed it further than most researchers were willing to go. His name was Max Tegmark, and the thought experiment he formalized became known as quantum suicide. Unlike a laboratory experiment, a thought experiment exists entirely within logic and mathematics. No one needs to build the apparatus. The purpose is to explore what a theory truly implies when taken seriously. The setup is deceptively simple. Imagine a machine connected to a quantum random number generator, a device whose outcomes originate from genuinely quantum events rather than hidden calculations. One common example is radioactive decay. A nucleus either decays within a given interval or it does not. Quantum mechanics provides probabilities, but it does not specify which outcome will occur in advance. Now, imagine a detector monitoring that event. If a decay is detected during the next second, the machine activates. If no decay occurs, nothing happens. The probabilities are evenly balanced. Half the possible outcomes lead one way, half lead the other. A physicist sits before the machine. The process begins. Within the Copenhagen interpretation, the situation appears straightforward. The wave function collapses. One outcome becomes real. There is a 50% chance the physicist survives and a 50% chance the physicist does not. The mathematics ends there. But the logic changes dramatically within the many worlds framework. There is no collapse. Both outcomes occur. In one branch, the detector registers a decay and the machine activates. In another branch, no decay is detected and the physicist remains unharmed. Each branch contains a different continuation of events. Both are equally part of reality. Now imagine repeating the process. A second trial occurs, then a third, then a fourth. With every quantum event, new branches emerge. Most contain outcomes where the physicist eventually dies. Yet after every round, there remains at least one branch where survival continues. The numbers become extreme very quickly. After 10 rounds, the probability of finding a surviving physicist within any particular branch falls below 1 in 1,000. After 20 rounds, it falls below 1 in 1,000,000. But probability is not existence. Even when a branch becomes extraordinarily unlikely, it still exists within the many worlds picture. Tegmark focused on a subtle detail. A dead observer has no experiences. No awareness remains inside that branch. No perspective continues there. Conscious observation exists only in branches where consciousness persists. From the inside, this creates an unusual asymmetry. An observer can witness survival. An observer cannot witness the absence of observation itself. Experience continues only along paths where experience remains possible. This leads to the controversial conclusion at the heart of quantum suicide. If branching truly occurs, and if conscious awareness follows only branches where it survives, then from the observer's own perspective, survival may be the only outcome ever encountered, regardless of how improbable those surviving branches become within the larger structure of reality. Imagine standing inside a vast library containing every book that could possibly be written. Most volumes would be unreadable collections of symbols. Many would contain no coherent language at all. Only a tiny fraction would hold meaningful stories. If you found yourself reading a sensible sentence, would that be surprising? Not really. You could only notice a readable book because you were already inside one. This simple idea sits at the heart of a principle that has become surprisingly important in modern cosmology. In 1973, physicist Brandon Carter gave it a formal name, the Anthropic Principle. At first glance, it appears almost trivial. Any universe we observe must be compatible with our existence, because if it were not, we would not be here to observe it. But beneath that simplicity lies something profound. The Anthropic Principle shifts how we think about probability. Instead of asking why we find ourselves in a universe capable of supporting observers, it reminds us that observation itself filters the possibilities. Countless alternative realities may be imaginable, yet only a subset can ever contain beings capable of asking questions about reality. Observer and observation become linked. This idea becomes especially important when physicists examine the remarkable precision of nature's fundamental constants. The strength of gravity, the masses of elementary particles, and the properties of electromagnetism all fall within narrow ranges that permit stars, chemistry, planets, and eventually life. Slight changes could produce sterile universes lacking complexity altogether. The anthropic principle offers one explanation. We find ourselves in a life permitting cosmos because only such a cosmos can contain observers. No design is required, no special privilege is assumed. The fact that you exist already limits the kinds of universes you could ever experience. The same reasoning can be applied on a much smaller scale. Within a branching framework, countless outcomes may occur across different realities. Some branches contain observers who continue living, others do not. But from the inside, awareness can only persist where awareness still exists. This introduces a concept known as observer selection bias. A selection bias occurs when the process of observing filters what can be observed. The filter is not external, it is built directly into the situation itself. You have already experienced this principle throughout your life, although usually in ordinary ways. There were illnesses you recovered from, dangerous intersections you crossed safely, flights that landed normally, moments where circumstances could have unfolded differently. Looking backward, survival often appears as a sequence of fortunate outcomes. But within the logic of quantum branching, another interpretation emerges. Your perspective exists only in histories where your perspective continues. You never experience the branches that exclude you because there is no version of you present to witness them. The argument does not claim invulnerability. It does not guarantee comfort. It simply follows the consequences of observer selection wherever they lead. If branches continue forming indefinitely, then conscious experience remains confined to those branches capable of supporting it. The remarkable question is how increasingly improbable those surviving paths may become as time moves forward. Take a sheet of paper and imagine writing a sentence across it. Then imagine crumpling the paper into a tight ball and throwing it into a fire. The ink disappears. The page blackens. The words seem gone forever. From an everyday perspective, they are. Yet, quantum physics tells a more subtle story. The information describing those words has not truly vanished. It has merely become dispersed into forms so complex that recovering it becomes practically impossible. The distinction between destroyed and unrecoverable turns out to be one of the deepest ideas in modern physics. At the heart of this idea lies a principle called unitarity. Unitarity is the rule that quantum evolution preserves information. As a quantum system changes through time, the total informational content remains intact. The details may spread, transform, and become entangled with their surroundings, but they are never erased from existence. This principle is built directly into Schrödinger's equation. The equation operates with remarkable symmetry. Given a complete description of a closed quantum system at one moment, the mathematics can evolve that system forward through time. In principle, it can also evolve the system backward. Every state remains connected to every previous state through an unbroken chain of information. Nothing is forgotten. For decades, one of the greatest physicists in history believed he had found an exception. Stephen Hawking argued that black holes destroy information. Matter falls through the event horizon, the boundary beyond which escape becomes impossible. Eventually, the black hole evaporates through a process known as Hawking radiation, a faint emission of particles predicted in 1974. The puzzle seemed unavoidable. If the black hole disappeared completely, where did the information go? This became known as the black hole information paradox. A paradox is a conflict between two established principles. In this case, quantum mechanics demanded preservation, while black hole evaporation appeared to demand destruction. The debate lasted for decades. Then, in 2004, Hawking publicly revised his position. After years of argument and a famous wager with physicist John Preskill at the California Institute of Technology, he accepted that information survives. The precise mechanism remains an active area of research, but the broader conclusion has gained wide support. Even black holes, nature's most extreme objects, do not appear capable of erasing information from reality. That realization changes how we think about existence itself. Every memory you possess corresponds to physical patterns. Every thought emerges from electrical activity, moving through networks of neurons. Every sensation leaves traces encoded within the state of matter and energy. These patterns are information in the most fundamental sense. But information occupies a special status in quantum theory. It can become scrambled beyond recognition. It can disperse across enormous systems. It can become woven into the wider fabric of the universe through countless interactions. Yet, according to the mathematics, it is not destroyed. Your body is temporary. Its components will eventually return to the wider cosmos. The atoms will separate and participate in new structures. But the informational history associated with those arrangements remains embedded within the evolving quantum state of reality itself, carried forward by laws that never permit true erasure. Every night, without effort, an entire universe appears behind your eyes. Memories surface, sounds acquire meaning, colors become experiences rather than wavelengths. Somewhere within the activity of the brain, matter transforms into awareness, and nobody knows how. For all the extraordinary successes of modern science, consciousness remains one of its deepest mysteries. We understand galaxies better than we understand subjective experience. We can trace the history of the universe back nearly 14 billion years. We can predict the behavior of particles with astonishing precision. Yet we still lack a complete explanation for the simple fact that experience exists at all. This puzzle became known as the hard problem of consciousness after philosopher David Chalmers introduced the term in 1995. The distinction matters. Scientists have made significant progress on what Chalmers called the easy problems. These include understanding attention, memory, language, perception, learning, and behavior. Difficult though they may be, they can be approached through observation and experiment. We can study neural circuits. We can monitor brain activity. We can investigate how information flows through biological systems. But another question remains untouched. Why does any of that processing feel like something from the inside? Electrical signals move through your brain every second. Chemical messengers cross microscopic gaps between neurons. Information is encoded, transformed, and transmitted. Yet none of these descriptions explain why there is an inner world accompanying the process. Why is there something it is like to be you rather than nothing at all? At present, science has no agreed answer. The dominant materialist view argues that consciousness emerges from sufficiently complex information processing. Under this perspective, awareness is not separate from the physical brain. It is what certain kinds of computation feel like from the inside. When the biological machinery stops functioning, consciousness ends because the process producing it has ended. Many researchers find this explanation compelling. Others believe it remains incomplete. One influential alternative is integrated information theory, often called IIT. Developed by neuroscientist Giulio Tononi, The theory proposes that consciousness corresponds to the degree of information integration within a system. Integration refers to how strongly different parts of a system depend upon one another. IIT measures this using a quantity called phi. Higher phi indicates greater integration and, according to the theory, greater consciousness. This shifts the discussion in an unusual direction. Consciousness becomes less about biology itself and more about informational structure. Another proposal goes further still. Physicist Roger Penrose and anesthesiologist Stuart Hameroff argue that consciousness may involve quantum processes occurring inside microscopic cellular structures called microtubules. Their model, known as orchestrated objective reduction or OR, suggests awareness emerges partly from quantum events rather than purely classical neural activity. The idea remains controversial, yet it continues to generate research and debate. What matters most is not which theory eventually proves correct. The crucial fact is that the connection between consciousness and the underlying laws of physics remains unresolved. The nature of awareness, the nature of information, and the nature of reality itself may be far more deeply connected than current science fully understands. Ancient Greece left physics an unexpected inheritance. More than 2,000 years ago, a philosopher named Zeno of Elea proposed a series of paradoxes suggesting that motion itself might be impossible. His arguments were philosophical rather than scientific, yet his name eventually became attached to one of the strangest effects ever discovered in quantum mechanics. The connection emerged in 1977. Physicists Baidyanath Misra and E. C. George Sudarshan were studying how unstable quantum systems evolve through time. Their calculations revealed a surprising possibility. Under certain conditions, repeatedly observing a quantum system could dramatically slow its evolution. In the extreme limit, the evolution could effectively stop. This became known as the quantum Zeno effect. To understand the idea, imagine a quantum system beginning in a particular state. Left alone, Schrödinger's equation predicts how that state changes over time. The system gradually spreads its probability across different possibilities, exploring alternative outcomes according to the rules of quantum mechanics. But frequent measurement alters the process. Each observation effectively checks whether the system remains in its original state. When these checks occur rapidly enough, the evolution is repeatedly interrupted before significant change can occur. The system is continually nudged back toward its starting condition. The effect is deeply counterintuitive. In classical physics, observation merely reveals what is already happening. A thermometer measures temperature without freezing it. A clock records time without stopping it. Observation is passive. Quantum mechanics is different. Observation becomes part of the dynamics. The act of obtaining information influences the physical behavior of the system being observed. For a radioactive atom, the consequences are remarkable. Theoretically, if measurements occur with sufficient frequency, the probability of decay can be driven toward zero. The atom becomes increasingly resistant to changing state. It does not remain stable because of a force or barrier. It remains stable because it is being continually measured. What began as a mathematical prediction eventually reached the laboratory. In 1989, physicist Wayne Itano and his colleagues at the National Institute of Standards and Technology conducted a famous experiment using beryllium ions. An ion is an atom carrying an electric charge. Their results demonstrated that frequent observation prevented the quantum system from making a transition it would otherwise have undergone. The prediction was confirmed. But nature rarely settles for a single surprise. Researchers later discovered the quantum anti-Zeno effect. Under different conditions, repeated observation can accelerate change rather than suppress it. Instead of slowing decay, measurement can increase the rate at which a system evolves. Both effects are now important in emerging technologies. Quantum computers rely on fragile quantum states that are constantly threatened by decoherence, the loss of quantum behavior through environmental interactions. Carefully controlled observation techniques can help preserve those states long enough for useful computation. The deeper implication extends beyond technology. Quantum systems cannot always be separated cleanly from the processes that observe them. Information, interaction, and evolution become intertwined. The observer is not simply standing outside the experiment. At the quantum level, observation itself becomes one of the forces shaping reality. Walk into a room and place a coffee mug on a table. Leave for an hour, then return. The mug remains exactly where you expect it to be. It is not smeared across multiple locations. It is not occupying several realities simultaneously. It appears solid, definite, and reassuringly ordinary. Yet the underlying laws governing its particles are quantum laws. This creates an apparent contradiction. If superpositions are real, and if quantum systems can exist in multiple possible states at once, why does everyday reality appear so classical? Why does the world present itself as a collection of definite objects rather than a haze of overlapping possibilities? The answer emerged through the work of physicist Wojciech Zurek and other researchers beginning in the 1980s. The key idea is called decoherence. Decoherence occurs whenever a quantum system interacts with its surroundings. A surrounding environment can include air molecules, photons, thermal radiation, nearby atoms, or virtually anything else. In practice, complete isolation is almost impossible. Every interaction matters. When a quantum system interacts with its environment, information about its state spreads outward. The system becomes entangled with countless surrounding particles. Entanglement means the properties of separate systems become linked in a way that must be described together rather than independently. The spreading happens extraordinarily fast. As information disperses through the environment, the different possibilities within a quantum superposition lose their ability to interfere with one another. Interference is the phenomenon that allows quantum possibilities to combine, reinforce, or cancel each other. Once decoherence occurs, that interference effectively disappears. The superposition has not vanished. It has become hidden. The information remains encoded within the larger quantum state, but it is distributed across so many environmental degrees of freedom that recovering it becomes practically impossible. The quantum behavior is still present beneath the surface. It is simply inaccessible. The timescales involved are astonishing. A carefully isolated electron can maintain quantum coherence, meaning its quantum properties remain intact for extremely long durations under suitable conditions, but larger objects behave very differently. For a dust particle suspended in ordinary air, decoherence can occur in roughly 10 to the power of negative 31 seconds. That interval is so brief that it effectively rounds to zero from a human perspective. The brain operates under even harsher conditions. Your nervous system is warm, chemically active, electrically dynamic, and constantly exchanging energy with its surroundings. Trillions of interactions occur continuously. Any delicate quantum coherence would be overwhelmed almost immediately by environmental entanglement. This is why branching, if it occurs, feels invisible. You do not sense alternative versions of reality because decoherence isolates branches from one another with extraordinary efficiency. Each branch evolves independently, carrying its own history and observations. The others become inaccessible. But decoherence is not a complete solution to every puzzle. It explains why the world appears classical despite its quantum foundations. It explains why quantum possibilities stop interfering. What it does not explain is why experience seems to follow a particular outcome. In many interpretations, that deeper question remains open, hidden behind the same veil that conceals the quantum world itself. Look up at the night sky, and it is easy to imagine that the challenge is distance. Galaxies lie millions of light years away. Clusters stretch across unimaginable expanses. The cosmos already feels larger than human intuition can comfortably hold. But size may not be the deepest surprise. Modern physics contains several independent ideas, suggesting that our universe could be only one region within a much larger reality. These ideas are often grouped together under the word multiverse, yet they do not describe the same thing. They emerge from different equations, different assumptions, and different branches of science. The simplest version is known as the Level 1 multiverse. This possibility arises if space extends infinitely far beyond the observable universe. We can only see a finite region because light has traveled a limited distance since the Big Bang. Beyond that horizon, space may continue forever. If the number of possible arrangements of matter is finite, while space is infinite, then arrangements must eventually repeat. The implication is startling. Somewhere unimaginably far away, there could exist regions containing galaxies identical to ours. Other regions might contain versions of Earth nearly indistinguishable from this one. The argument does not require exotic physics. It follows from probability applied to infinite space. A second possibility emerges from cosmology. According to inflation theory, the infant universe underwent a brief period of extraordinarily rapid expansion. Physicists, such as Alan Guth, André Linde, and Alexander Vilenkin, developed models suggesting that inflation may never completely stop. Instead, different regions exit inflation at different times, forming separate bubble universes. This is called the Level 2 multiverse. Each bubble may possess different physical properties. The strengths of forces, particle masses, or even the laws governing matter could vary from one cosmic region to another. Entire universes become isolated islands floating within a larger, inflating background. Then comes the Level 3 multiverse. This is the quantum branching picture associated with many worlds. Instead of separate regions occupying distant locations, branching occurs continuously through quantum events. Every possible outcome unfolds within its own branch of reality. The branching happens everywhere and all the time, woven directly into the fabric of quantum mechanics. But Max Tegmark proposed something even more ambitious. The Level 4 multiverse suggests that every mathematically consistent structure exists physically. Mathematics is not merely a language describing reality. Mathematics becomes reality itself. Every self-consistent mathematical system corresponds to an actual universe, whether or not it resembles our own. This is the most speculative level. Many physicists remain unconvinced. The important point is that these frameworks are distinct. A cosmologist may accept infinite space while rejecting many worlds. Another researcher may support eternal inflation but reject the mathematical universe. Agreement on one level does not require agreement on the others, yet all of them point in a similar direction. The observable universe, vast as it already appears, may represent only a tiny fragment of a much larger structure. Even before questions of consciousness enter the discussion, modern physics has already opened the possibility that reality extends far beyond the single cosmic stage we ordinarily imagine ourselves inhabiting. There comes a point in certain scientific ideas where the mathematics continues calmly forward while intuition quietly refuses to follow. This is one of those places. Up to now, the logic has remained relatively straightforward. If branching realities exist, and if conscious observers can only experience branches in which consciousness continues, then awareness appears naturally linked to survival. But what happens when survival becomes extraordinarily unlikely? The question grows sharper with age. A healthy young adult surviving another year requires nothing unusual. Ordinary biology is sufficient. Decades pass, the probabilities remain comfortable, but eventually biology becomes fragile. Cells accumulate damage, repair mechanisms weaken, disease becomes more common. The number of branches containing continued survival gradually decreases, yet within the branching framework, even highly improbable outcomes remain possible. A person reaching 90 years of age already occupies a narrower set of survival histories than someone reaching 40. At 120 years old, the surviving branches become rarer still. Maintaining biological function requires increasingly unusual combinations of events, fortunate mutations, unexpected recoveries, and unlikely circumstances. But probability never becomes zero. This is where an old idea from statistical physics enters the story. In the late 19th century, physicist Ludwig Boltzmann explored the relationship between order and disorder. His work helped establish modern thermodynamics, the study of energy and entropy. Entropy is a measure of disorder within a system. Left alone, systems tend toward greater disorder over time. Yet fluctuations occasionally occur. Given enough time, particles can briefly arrange themselves into highly ordered states purely by chance. The odds are tiny, but not non-existent. Boltzmann realized that in an enormous universe existing for vast stretches of time, even extraordinarily unlikely arrangements would eventually appear. The concept later evolved into what physicists call a Boltzmann brain. A Boltzmann brain is a hypothetical conscious observer formed spontaneously through random fluctuations of matter and energy. Not an evolved organism, not a biological being, simply a configuration of particles that happens, for a brief moment, to possess the structure required for conscious experience. The idea sounds absurd. That is precisely why physicists pay attention to it. If certain cosmological models predict that Boltzmann brains vastly outnumber ordinary observers, then something may be wrong with those models. The concept functions partly as a warning sign, revealing unexpected consequences hidden within theoretical frameworks. But when combined with quantum immortality, the implications become stranger still. If survival branches must always exist, then increasingly improbable circumstances may eventually dominate the remaining paths available to consciousness. Survival might cease depending on ordinary biological processes. Instead, awareness could persist through increasingly exotic physical configurations, not because such outcomes are likely, because they remain possible. This is one reason many physicists who find aspects of many worlds persuasive remain skeptical of quantum immortality itself. Following the logic to its furthest conclusion does not lead toward familiar notions of eternal life. It leads toward scenarios so unusual that they challenge our understanding of identity, continuity, and what it would even mean for consciousness to persist. In that sense, the endpoint becomes stranger than the problem it was meant to solve. On a laboratory bench sits a deceptively simple arrangement. A source emits particles. A barrier contains two narrow openings. Beyond it rests a screen waiting to record whatever arrives. Nothing about the setup appears revolutionary. Yet this modest experiment has transformed our understanding of reality more profoundly than almost any other scientific test ever performed. It is known as the Double Slit Experiment. Imagine firing electrons one at a time toward the barrier. Classical intuition suggests a straightforward outcome. An electron should travel through the left slit or the right slit and strike the screen accordingly. Given enough electrons, we would expect two concentrated bands to appear behind the openings. That is not what happens. When both slits remain open and no attempt is made to determine the electron's path, the screen gradually reveals an interference pattern. Bright regions alternate with dark regions in a series of bands. This pattern is characteristic of waves. It resembles the ripples created when water passes through two openings and overlaps with itself. The implication is extraordinary. Each electron behaves as though it explores both paths simultaneously. Even when electrons are emitted individually, separated in time, the interference pattern still emerges. Somehow, each particle acts like a wave spread across multiple possibilities before arriving at the detector. But now the experiment changes. A measuring device is placed near the slits. The goal is simple: determine which opening each electron passes through. The slits remain open. The apparatus does not physically block the path, yet the result transforms completely. The interference pattern disappears. The electrons now behave like localized particles traveling through one slit or the other. The wave-like behavior vanishes as soon as information about the path becomes available. What changed? Not the barrier, not the screen, not the electron source. Information changed. The mere possibility of knowing which route the electron took alters the outcome. The experiment has been repeated with photons, atoms, and increasingly large molecules. In 1999, researchers at the University of Vienna demonstrated quantum interference using buckyballs, spherical molecules composed of 60 carbon atoms. Even objects, far larger than individual particles, exhibited the same fundamental behavior. The mystery deepened further that same year. Physicist Marlon Scully and his colleagues explored a variation called the quantum eraser. In this version, path information is recorded and then erased before the final observation is analyzed. Remarkably, when the which path information becomes unavailable, the interference pattern reappears. The details are subtle. No signal travels backward through time. No paradox violates causality. Yet the experiment demonstrates something equally remarkable. The behavior observed depends not simply on physical interactions, but on what information remains available within the system. This is why the double slit experiment continues to occupy such a central place in quantum theory. It repeatedly reveals that information and physical reality are deeply intertwined. At the quantum level, particles do not merely exist within the universe. They exist within a structure where what can be known helps determine what can occur, binding observation and reality together in ways that still challenge our most basic intuitions. Imagine separating two objects by an impossible distance. One drifts beyond planets, beyond stars, perhaps even beyond the visible edge of a galaxy. The other remains nearby. Common sense tells us that increasing distance weakens connection. The farther apart things become, the less influence they can have on one another. Quantum mechanics disagrees. Among all the discoveries of modern physics, few disturbed Albert Einstein more deeply than quantum entanglement. He famously dismissed it as spooky action at a distance, a phrase that revealed both skepticism and discomfort. Einstein believed that deeper laws must exist beneath quantum theory, hidden variables that would restore a more intuitive picture of reality. Nature had other plans. Entanglement occurs when two quantum particles interact in such a way that their states become linked. A quantum state is the complete mathematical description of a particle's properties. Once entangled, the particles can no longer be fully described independently. They become parts of a larger system, even after moving far apart. The connection survives separation. Measure one particle, and you immediately know something about the other. If the particles were prepared in a particular entangled state, determining one result automatically determines the corresponding result of its partner. At first, many physicists suspected hidden information might explain the phenomenon. Perhaps the particles secretly carried instructions established before they separated. If so, the correlations would be remarkable but not revolutionary. Experiments eventually tested this possibility. In 1982, physicist Alan Aspect and his team in Paris performed a series of increasingly sophisticated measurements using entangled photons. Their results strongly supported the quantum predictions and ruled out broad classes of hidden, variable explanations. The correlations were real, and they exceeded what classical theories could produce. The implications were profound. Later experiments pushed the phenomenon even further. In 2017, the Chinese satellite Micius distributed entangled photons across distances exceeding 1,200 kilometers. The correlations remained intact across continental scales, demonstrating that entanglement survives distances far beyond anything achievable in ordinary laboratories. But an important limit remains. Entanglement does not allow faster than light communication. No message can be transmitted instantaneously through the connection. Relativity remains safe. What changes is not communication but correlation. The universe appears structured in a way that classical physics never anticipated. Recognition eventually followed. In 2022, Elaine Aspect, John Clauser, and Anton Zeilinger received the Nobel Prize in Physics for pioneering work that transformed entanglement from a philosophical puzzle into an experimentally verified feature of nature. Within the many worlds framework, the phenomenon takes on a different appearance. Entanglement becomes the mechanism through which quantum histories become linked. Separate systems evolve together because they are components of a shared quantum state. No invisible signal crosses the distance. The connection already exists. And perhaps that is the deepest lesson. The boundaries we perceive may be less fundamental than they appear. Every atom in your body has interacted with countless others throughout cosmic history. Light has touched your skin. Air has entered your lungs. Matter has exchanged information with matter for billions of years. At the quantum level, separation becomes harder to define, and the universe begins to resemble a vast web of relationships rather than a collection of isolated things. Press your hand against a wall. The sensation feels simple enough. Solid matter meets solid matter. Your hand stops moving. The wall resists. Nothing appears mysterious about the interaction. Yet beneath that ordinary moment lies one of the most important rules in the universe. Without it, neither your hand nor the wall would exist in anything resembling their current form. The rule is called the Pauli exclusion principle. It was proposed in 1925 by Austrian physicist Wolfgang Pauli while scientists were struggling to understand the architecture of atoms. At first glance, the principle sounds technical. Its consequences, however, reach into every aspect of physical reality. The principle states that no two identical fermions can occupy the same quantum state simultaneously. A fermion is a category of particle that includes electrons, protons, and neutrons, the fundamental building blocks of ordinary matter. A quantum state describes the complete set of properties characterizing a particle within a system. The exclusion principle forbids identical fermions from sharing precisely the same state. This simple restriction shapes the structure of everything around us. Inside atoms, electrons occupy different energy levels rather than collapsing into a single lowest state. Because they must remain distinct, atoms develop layered structures with complex electron arrangements. Chemistry emerges from those arrangements. Molecules form, matter acquires diversity. Without the exclusion principle, the periodic table would disappear. So would chemistry. Atoms would lose their structure, and the intricate complexity necessary for life could never arise. The effect extends far beyond atomic architecture. When you push your hand against a table, the resistance you experience is not simply a matter of particles touching. At the microscopic level, electrons within your hand and electrons within the table are prevented from occupying identical quantum states. The exclusion principle contributes directly to the solidity of matter itself. The universe gains structure because certain arrangements are forbidden. Every organ in your body reflects that restriction. Every protein, every strand of DNA, every neuron participating in conscious thought depends upon quantum states remaining distinct. The stability of your physical form emerges partly from an endless enforcement of this rule across countless particles. But the principle carries another implication that often receives less attention. Your exact quantum configuration is unique. Not merely rare, unique. The precise arrangement of particles composing your body at this moment cannot be duplicated within your immediate surroundings. Quantum mechanics itself prevents identical fermions from stacking into the same states. The detailed structure that constitutes you occupies its own exclusive location within reality. This does not prevent distant similarities. In an infinite cosmos, or within certain multiverse models, configurations resembling you could exist elsewhere. Vast separations allow classical probability to operate differently. Locally, however, the situation is more restrictive. You occupy a singular position within the quantum landscape. The laws governing matter do not merely permit your existence, they carefully define it. Every particle in your body participates in an arrangement that can occur exactly here, exactly now, and nowhere else. In that precise quantum sense, your existence is not only improbable, it is exclusive, protected by one of the deepest principles in all of physics. Imagine attempting to write a single equation that describes everything. Not a planet, not a star, not even an entire galaxy. Everything. Every particle that has ever existed, every field permeating space, every burst of radiation, every living creature, every thought, every moment across cosmic history. The ambition sounds impossible, yet this was precisely the direction Hugh Everett's ideas pointed. Rather than applying quantum mechanics to isolated systems, Everett asked what would happen if the theory were applied universally, without exception. If Schrödinger's equation truly governs reality, why should it stop at laboratory boundaries? Why not apply it to the entire cosmos? In ordinary quantum mechanics, a wave function describes the state of a system. A wave function is a mathematical object containing all the information available about that system. It encodes possibilities, probabilities, and relationships between measurable properties. Everett extended this idea dramatically. He proposed a universal wave function, a single quantum description encompassing the entirety of reality. Every particle, every quantum field, every interaction throughout the cosmos would be part of one immense mathematical structure, evolving according to the same fundamental rules. No outside observer is required. No special measurement event is needed. The universal wave function simply evolves continuously through Schrödinger's equation. Branches emerge naturally as quantum interactions unfold. The process does not pause. It does not select favored outcomes. It generates the full network of possible histories permitted by the laws of physics. Within this picture, you are not separate from the equation. Your body is part of it. Your brain is part of it. Even your conscious experience becomes part of its unfolding structure. What you perceive as a personal life corresponds to a particular path through an unimaginably vast landscape of quantum possibilities. Subjective experience becomes the inside view of a specific branch evolving within the larger wave function. This perspective led some physicists toward even more radical conclusions. Julian Barbour, among others, has argued that time itself may not be fundamental. According to this view, the sensation of moments flowing from past to future could emerge from relationships embedded within the wave function rather than from an external cosmic clock. The implication is unsettling. What if all moments exist equally? Instead of a moving present advancing through time, reality could consist of an enormous structure containing every configuration simultaneously. The feeling of progression would arise from consciousness encountering those configurations in a particular sequence. Within such a framework, the distinction between past and future becomes less absolute than everyday experience suggests. The universal wave function contains every branch, every event, and every observer allowed by the underlying laws. It does not privilege one version of reality over another. It includes them all within the same mathematical entity. That includes you, not merely the version listening to these words, but every version associated with every branch generated throughout your history. Each exists as part of the larger structure. The wave function continuously evolves, rearranges, and branches, yet nothing is removed from its description. Possibilities become histories, histories become patterns, and the mathematical framework retains them all within the vast quantum architecture of the universe itself. Notice what your memories have in common. Everyone points backward. You remember childhood, yesterday's conversation, the meal you ate earlier today. You never remember tomorrow. You never recall next year. Experience unfolds in a single direction so naturally that we rarely stop to question it. Yet physics does. The deeper we look into the laws governing reality, the stranger this becomes. Many of the fundamental equations describing nature show no preference for past or future. If you were shown a film of certain microscopic interactions running backward, the equations would often remain perfectly valid. This includes quantum mechanics. Schrödinger's equation, the mathematical foundation underlying much of modern quantum theory, works equally well in both temporal directions. The equation itself contains no built-in arrow pointing from yesterday toward tomorrow. It does not distinguish between forward and backward flow. So why does time seem so directional? The answer appears connected to a concept called entropy. Entropy is a measure of how many possible arrangements a system can have. Higher entropy corresponds to greater disorder and a larger number of possible configurations. Lower entropy corresponds to greater order and fewer possibilities. A simple example helps. Imagine a pristine sandcastle on a beach. Wind and waves gradually erode its structure. Grains scatter. The organized shape disappears into a less ordered arrangement. The process happens naturally because there are vastly more disordered ways for the sand to exist than organized ones. The same principle operates throughout the universe. Stars fuse hydrogen into heavier elements while releasing radiation into surrounding space. Living organisms consume concentrated energy and produce heat. Galaxies evolve, structures form, and eventually decay. Everywhere we look, entropy tends to increase. This tendency is formalized in the second law of thermodynamics. The law states that the total entropy of a closed system will increase or remain constant over time. It never spontaneously decreases on large scales. The universe continuously moves toward states with greater numbers of possible configurations. That progression creates the sensation of temporal flow. You remember the past because it was more ordered than the present. Records, memories, and physical traces all depend upon low entropy conditions. The future has not yet generated those records. It contains more possible arrangements and therefore remains unknown. But a deeper mystery remains. Why did the universe begin in such an extraordinarily ordered state in the first place? Observations indicate that the early universe emerging from the Big Bang possessed remarkably low entropy. This initial condition provided the starting point from which entropy could steadily increase for billions of years. Without that beginning, the arrow of time would not exist as we experience it. Physicist Sean Carroll has argued that this may be one of the deepest unanswered questions in science. Dark matter is mysterious. Quantum gravity remains unfinished. Yet understanding why the universe began in a low entropy state may be even more fundamental. It is the reason reality feels like a sequence of events rather than a static mathematical structure. The growth of entropy transforms timeless equations into a cosmos that appears to move, change, remember, and endure. Stand beneath a clear night sky, and everything appears calm. The stars hold their positions. Constellations seem permanent. The heavens give the impression of stability, as though the universe were a vast stage whose scenery changes only slowly. But appearances are deceptive. At the largest scales, the cosmos is not standing still. Space itself is stretching. Galaxies are drifting apart. Distances between immense structures continue to grow with every passing moment. More surprising still, the expansion is accelerating. This discovery arrived unexpectedly in 1998. Two independent teams studying distant Type Ia supernovae reached the same conclusion. One group was led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees. Type Ia supernovae serve as reliable cosmic distance markers because they explode with nearly uniform brightness. The observations revealed something astonishing. The distant supernovae appeared dimmer than expected. They were farther away than standard cosmological models predicted. The universe was not slowing under gravity's influence. It was speeding up. Something was pushing space outward. Physicists gave this unknown influence a name: dark energy. The term describes whatever is driving cosmic acceleration. It is not dark because it absorbs light. It is dark because its nature remains unknown. Current observations suggest dark energy constitutes roughly 68% of the total energy content of the universe. Most of reality appears to be something we do not yet understand. As expansion continues, the cosmic landscape changes dramatically. Galaxies outside our local group will gradually disappear from view. They are not traveling through space faster than light. Instead, the space between us and them expands so rapidly that their light can no longer reach us. The universe grows lonelier. Future observers may see only their own gravitationally bound collection of galaxies, unaware that trillions of others once filled the observable cosmos. The timescales involved are almost beyond imagination. In approximately 100 trillion years, star formation will largely cease as available fuel becomes exhausted. Existing stars will gradually burn out. Darkness will spread through the galaxies. Far later, if certain theoretical predictions are correct, protons may decay after roughly 10 to the power of 40 years. Ordinary matter itself would slowly dissolve. The future stretches onward. Black holes persist longer than stars. A black hole with the mass of our Sun requires roughly 10 to the power of 67 years to evaporate through Hawking radiation. The largest supermassive black holes may survive until approximately 10 to the power of 100 years before finally disappearing. What remains after that is a state known as heat death. Heat death does not involve fire or destruction. It is maximum entropy. Energy remains present, but it becomes so evenly distributed that no useful work can occur. No engines run, no stars shine, no large-scale structures emerge. The universe approaches thermal equilibrium. Against that backdrop, questions about consciousness acquire a cosmic scale. If awareness depends upon organized information processing, what happens when the cosmos itself approaches a state where organization becomes increasingly difficult to sustain? The future of consciousness becomes inseparable from the future of the universe that produced it. Enrico Fermi was attending a casual lunch in 1950 when he suddenly asked a question that continues to echo through modern science. The conversation had wandered across flying saucers, interstellar travel, and the possibility of extraterrestrial life. Then Fermi paused and asked a simple question: where is everybody? The question became known as the Fermi Paradox. A paradox is an apparent contradiction between what we expect and what we observe. In this case, the contradiction emerges from the sheer scale of the cosmos. The universe is approximately 13.8 billion years old. Our galaxy alone contains somewhere between 100 billion and 400 billion stars. Many of those stars are older than the Sunday. The numbers are difficult to ignore. Observations from the Kepler Space Telescope transformed the discussion even further. Kepler revealed that planets are common rather than exceptional. Most stars appear to host planetary systems. Many possess worlds orbiting within regions where liquid water could potentially exist on a planetary surface. Astronomers call this the habitable zone. Even conservative estimates suggest millions of potentially habitable planets reside within the Milky Way alone. Extend the calculation across the observable universe, and the numbers become staggering. Opportunities for life appear almost limitless, yet the sky remains silent. We have detected no confirmed extraterrestrial signals, no verified probes, no unmistakable technological artifacts, no evidence of galaxies spanning civilizations. Despite decades of searches, the universe offers no clear answer. This silence becomes increasingly difficult to explain. One proposed solution is known as the Great Filter. A filter is a barrier preventing most civilizations from progressing to detectable scales. The filter could lie behind us. Perhaps the emergence of complex life is extraordinarily rare. Perhaps intelligence almost never develops. That possibility is reassuring. Another possibility is not. The filter may lie ahead. Civilizations could routinely encounter challenges that prevent long-term survival. Environmental collapse, technological self-destruction, resource exhaustion, or unknown cosmic hazards might eliminate most advanced societies before they spread widely through the galaxy. The uncertainty remains profound. When viewed through the lens of observer selection, the puzzle acquires an additional layer. Conscious observers naturally find themselves in histories where conscious observers continue to exist. Individual survival branches may remain available, but what about entire civilizations? What if the branches allowing long-term technological survival are exceptionally uncommon? From the inside, a civilization would continue experiencing its own persistence. Its members would naturally inhabit histories in which they survived previous dangers. Yet when viewed across the broader cosmic landscape, most civilizations might still disappear before becoming visible across interstellar distances. The result would look remarkably similar to what we observe. A universe rich in opportunities for life, yet strangely quiet. The Fermi Paradox does not prove anything about quantum immortality or branching realities, but it highlights an uncomfortable possibility. Survival may feel normal from within any surviving perspective, while extinction remains the dominant outcome across the larger tapestry of cosmic history. The silence between the stars may not indicate absence. It may reveal how rare enduring civilizations truly are. Imagine removing every familiar ingredient from reality. Remove planets, remove stars, remove atoms, remove energy, remove even space and time themselves. What remains? For most of history, the answer would have been nothing, but a growing number of physicists and philosophers have suggested a different possibility. What remains is information. This idea sits at the edge of modern physics, mathematics, and philosophy. It asks whether the physical world we experience is not the foundation of reality at all, but instead the visible expression of something deeper and more abstract. Max Tegmark pushed this possibility further than almost anyone before him. His mathematical universe hypothesis proposes that mathematics is not merely a language humans invented to describe nature. Mathematics is nature. The equations are not representations of reality. They are reality. It is an extraordinary claim. Under this view, every mathematically consistent structure exists, not symbolically, not potentially, actually. Our universe is simply one self-consistent mathematical structure among an unimaginable collection of others. We experience this particular structure because it contains observers capable of experiencing it. In this framework, physical existence and mathematical existence become the same thing. The distinction disappears. A universe built from different equations would be just as real to the observers living inside it. Their laws of nature might differ dramatically from ours. Their particles, dimensions, and forms of complexity could be unfamiliar beyond imagination. Yet, from within their own structure, everything would feel as concrete and physical as our world feels to us. The proposal sounds radical because it overturns ordinary intuition, but mathematics already occupies a peculiar position in science. Equations developed for purely abstract reasons often describe physical reality with astonishing accuracy decades later. Patterns discovered on paper repeatedly appear woven into nature itself. Why should that be? John Archibald Wheeler spent years considering that question. Wheeler helped develop nuclear physics, explored black holes, and trained generations of physicists. Late in life, he became increasingly fascinated by the role of information. His famous phrase was simple: it from bit. The phrase suggested that every physical thing, every particle, every field, every event emerges from information at the deepest level. A bit is the simplest unit of information, a yes or no answer, a binary choice, Wheeler wondered whether reality itself might ultimately be built from countless informational distinctions. The idea continues to influence modern research. Quantum computing, black hole thermodynamics, and theories of quantum gravity increasingly treat information as something fundamental rather than secondary. Matter may not be the deepest layer. Space may not be the deepest layer. Even time may not occupy the foundation. Information remains. Within that possibility, consciousness takes on a different character. Rather than being a mysterious property produced by matter, it becomes a specific pattern unfolding within an informational structure. A mind is not separate from reality. It is one way reality organizes information into experience, allowing the universe to become aware of itself from the inside. A curious shift has taken place in modern physics. The deeper researchers probe beneath matter, energy, and space itself, the more often they encounter a language that sounds less like machinery and more like computation. Information appears everywhere. Quantum states store information. Black holes appear to preserve information. Theories of gravity increasingly describe reality through informational relationships. Against that backdrop, an old philosophical idea returned wearing modern mathematical clothing. What if reality is not the deepest level of reality? What if the universe we experience exists inside a larger framework, much as a virtual world exists inside a computer? In 2003, philosopher Nick Bostrom published a paper that transformed this possibility from science fiction into a subject of serious academic discussion. His argument became known as the simulation hypothesis. The logic begins with technological progress. Human civilization has advanced from the first electronic computers to artificial intelligence and virtual environments in only a few generations. If technological development continues for thousands or millions of years, future civilizations could possess computational capabilities beyond anything we can currently imagine. Bostrom proposed a trilemma, a three-way logical choice. Either almost every technological civilization becomes extinct before reaching that stage, or advanced civilizations survive but choose not to create detailed simulations containing conscious beings. Or such simulations become common, making simulated observers vastly more numerous than biological ones. If conscious simulations are abundant, statistical reasoning leads somewhere uncomfortable. Most minds would exist inside simulations. From the perspective of an observer living within one of those worlds, everything would appear normal. Mountains would feel solid. Time would seem continuous. Physical laws would operate consistently. The simulated inhabitants would have no direct way to determine whether their reality was fundamental or generated. The distinction would be hidden, but some researchers have wondered whether traces might remain. In 2012, physicist Silas Bean and colleagues explored whether a simulated universe operating on an underlying computational grid could leave subtle signatures in extremely high-energy cosmic rays. Their work did not prove the hypothesis, yet it demonstrated that parts of the idea can be examined scientifically. The search continues. Meanwhile, public figures have drawn attention to the concept. Elon Musk famously argued that the odds of living in base reality may be extraordinarily small. Astrophysicist Neil deGrasse Tyson suggested the probability could be significant. These statements are not measurements. They are reflections on a philosophical argument rather than experimental conclusions. Still, the discussion persists because it emerges naturally from deeper questions about information and existence. If reality is fundamentally informational, a simulation becomes conceptually possible. If minds are information patterns Rather than special substances, they could, in principle, exist within many different physical substrates. But the hypothesis introduces a deeper layer of mystery. Suppose the universe is simulated. What then? The question does not disappear. It moves upward. The reality containing the simulation would require its own laws, its own structure, and perhaps its own observers. That larger reality might itself be embedded within another. The chain could continue indefinitely, each world nested inside a broader one, like reflections stretching beyond sight through a corridor of mirrors. For all the vast theories we have explored, from branching universes to mathematical realities, there remains a simpler place to look. We can examine the organ that produces every thought, memory, dream, and sensation you have ever known: the human brain. Modern neuroscience approaches consciousness from a practical direction rather than asking what consciousness ultimately is. Researchers investigate how it behaves, where it appears, and what happens when the biological systems supporting it begin to fail. The prevailing conclusion is straightforward. Consciousness depends on brain activity. Neurons communicate through electrochemical signals, forming enormous networks that process information continuously. Every sight, sound, memory, and emotion emerges from these interactions. When those interactions cease permanently, mainstream neuroscience holds that conscious experience ends as well. This remains the consensus position. Yet the transition from life to death is not as sharply defined as it once seemed. For centuries, the stopping of the heart marked the end of life. Today, we know otherwise. Clinical death, the cessation of heartbeat and breathing, can sometimes be reversed through modern medical intervention. Individuals have returned after several minutes without circulation, occasionally reporting vivid experiences during the period when they appeared lifeless. The distinction is important. Brain death, not cardiac arrest, is the accepted medical definition of irreversible death. Brain death occurs when all brain function has permanently ceased and cannot be restored. Under current scientific understanding, recovery from true brain death does not occur. But the moments surrounding that boundary continue to raise difficult questions. Near-death experiences, often abbreviated as NDEs, have been reported by roughly 10 to 20% of cardiac arrest survivors. Accounts emerge from many cultures and backgrounds. Despite differences in personal beliefs, recurring patterns appear again and again. People describe leaving their bodies. They describe moving through darkness. Many report encountering a bright light, revisiting important memories, or experiencing an overwhelming sense of calm. These reports do not automatically reveal what caused the experiences. They do, however, point toward a consistent phenomenon that demands explanation. Researchers have searched for clues within the dying brain itself. In 2014, neuroscientist Jimo Borjigan and colleagues at the University of Michigan recorded the brain activity of dying rats following cardiac arrest. Unexpectedly, they observed a burst of highly organized gamma wave activity during the final seconds. Gamma oscillations are often associated with conscious awareness, perception, and information integration. The brain appeared briefly more coordinated, not less. Years later, similar findings emerged in humans. In 2023, Borjigan's team reported recordings from 4 patients who experienced cardiac arrest while under neurological monitoring. Several showed intense gamma activity, concentrated in regions linked to visual processing, dreaming, memory retrieval, and the sense of self. The findings are intriguing, but interpretation remains difficult. These studies do not demonstrate that consciousness survives death. They show that the dying brain may remain unexpectedly active during its final moments. Such activity could generate powerful internal experiences. It could explain many reported features of near death experiences through known biological mechanisms, or it may point toward processes we do not yet fully understand. The measurements are real. The meaning behind them remains unsettled. Among the many attempts to explain consciousness, few are as ambitious as the proposal developed by Roger Penrose and Stuart Hameroff. It does not merely connect consciousness to the brain. It suggests that consciousness emerges from quantum processes operating deep within the fabric of physical reality itself. The idea begins with a dissatisfaction. Roger Penrose spent decades working at the highest levels of mathematical physics. He helped reveal the nature of black holes, explored singularities in general relativity, and contributed profoundly to our understanding of spacetime. Yet he became increasingly convinced that consciousness could not be explained entirely through ordinary computation. His concern centered on reasoning itself. Human beings seem capable of recognizing certain mathematical truths directly, even when those truths cannot be derived through purely algorithmic procedures. Penrose argued that if the mind were nothing more than a conventional computer, every act of thought would ultimately reduce to fixed computational rules. He believed something was missing. In books published in 1989 and 1994, Penrose proposed that conscious understanding may depend on processes that are fundamentally non-computational, meaning they cannot be reproduced by any ordinary algorithm, regardless of complexity. But where could such processes occur? Penrose suspected the answer lay at a boundary physics has not yet fully crossed: the intersection between quantum mechanics and gravity. Existing theories describe each domain extraordinarily well in isolation, yet they remain difficult to unite into a single framework. The brain, he suggested, might somehow exploit that unfinished territory. Stuart Hameroff, an anesthesiologist interested in the biological basis of awareness, proposed a mechanism. Inside neurons are microscopic protein structures called microtubules. Traditionally, these structures are understood as part of the cell's internal architecture and transport system. Hameroff argued they might also support delicate quantum processes. Together, the two researchers developed a model known as orchestrated objective reduction, usually shortened to ORC-OR. According to the theory, quantum states arise within microtubules and evolve coherently for brief periods. Quantum coherence means multiple possibilities remain linked as part of a single quantum state. Eventually, these states undergo a physical reduction process connected to space-time geometry itself, generating moments of conscious experience. The proposal remains controversial. Many neuroscientists remain unconvinced that quantum coherence could survive within the warm and noisy environment of the brain. Others argue that conventional neural mechanisms may already explain consciousness without requiring exotic physics. Yet research continues. In recent years, studies have reported quantum effects in biological systems once thought incapable of supporting them. Quantum coherence has been observed in photosynthetic organisms, bird navigation systems, and other living structures. Investigations into microtubules have produced findings that some researchers view as compatible with aspects of ORCH-OR. The evidence remains incomplete. But if consciousness truly depends on quantum information, the implications become profound. Quantum information possesses unusual properties. Under accepted physical principles, it cannot simply vanish from existence. It transforms, it disperses, it becomes encoded in larger systems. If OR ultimately proves correct, the question would no longer be whether consciousness involves quantum processes. The deeper mystery would become where those processes reside once the biological structures that organize them have fallen silent. Stand beneath a tree and take a slow breath. The oxygen entering your lungs may have passed through leaves only weeks ago. The carbon leaving your body may someday become part of a forest, a shell resting on an ocean floor, or the wing of an insect moving through summer air. Nothing remains isolated for long. The universe is a vast exchange. From the perspective of everyday life, death appears to be an ending. A body ceases to function. Cells break apart. Structures that once maintained themselves dissolve into the environment. Over time, recognizable traces disappear. But physics describes a different process. Not disappearance, redistribution. Every atom in your body participates in an ongoing cycle of transformation. Carbon, oxygen, nitrogen, phosphorus, and countless other elements move outward into the surrounding world. Soil receives them, water carries them, living organisms incorporate them. Matter continues its journey through new forms and new systems. The process never stops. Yet beneath these visible exchanges lies something more subtle. Modern quantum theory suggests that physical systems contain information describing their states and relationships. Information in this context does not mean words, memories, or knowledge. It means the complete physical description of a system and how its components are connected. According to accepted quantum principles, that information is not destroyed, it evolves. As your body interacts with the environment, information becomes distributed across an ever-growing network of particles. Photons scatter, molecules collide, atoms exchange energy. Each interaction creates new correlations while preserving the deeper informational structure encoded within the universal quantum state. The original pattern becomes extraordinarily difficult to recover, practically impossible. But impossible to reconstruct is not the same as erased. This distinction sits at the heart of modern debates about information conservation. When physicists say information is preserved, they do not mean it remains accessible in any useful form. They mean the universe never truly forgets. Every interaction leaves traces woven into the evolving structure of reality itself. The idea became especially important during debates surrounding black holes. Stephen Hawking initially argued that information falling into a black hole could disappear forever. Decades of research challenged that conclusion. By 2004, Hawking publicly accepted that information must survive, even if the mechanism remained difficult to describe. That shift transformed more than black hole physics. It reinforced a broader principle. Information appears fundamental. Some researchers extended this reasoning through the holographic principle developed from work by Gerard Hooft and Leonard Susskind during the 1990s. The principle suggests that all information contained within a region of space may ultimately be encoded on its boundary surface, much as a hologram stores a three-dimensional image on a two-dimensional medium. If that picture reflects reality, the universe may possess a far deeper informational architecture than appearances suggest. Within that framework, the pattern that once constituted you is never deleted. It becomes part of the larger informational tapestry of the cosmos. Your body returns to the universe physically, while the traces of every interaction remain woven into its evolving quantum structure, carried forward as part of the ongoing story written across reality itself. Set aside distant futures for a moment. Forget cosmic endings, black holes, and the ultimate fate of consciousness, bring your attention back to something much closer. This moment. The words you are reading now exist within a single thread of experience. You perceive one sequence of events unfolding in one direction. Your memories form a continuous story. Your identity feels unified. Your life appears to follow a single path through time. That experience feels absolute. Within the many worlds interpretation, however, it may be only one strand among countless others. Every second, quantum events occur throughout your body and the environment around you. Photons scatter from surfaces, molecules collide, neurons exchange signals, particles interact according to probabilities described by quantum mechanics. If branching is real, every unresolved quantum possibility contributes to an ever-expanding structure of diverging histories. The process never pauses. It happens constantly. Long before this moment arrived, branches emerged in which tiny differences accumulated into larger consequences. A conversation unfolded differently. A decision shifted slightly. A chance encounter occurred or failed to occur. The details need not be dramatic. Small changes can compound over time, creating lives that gradually diverge from one another. Some branches remain nearly identical. Others drift apart. Within those alternate histories exist versions of you sharing the same childhood, many of the same memories, and much of the same personality. They began from the same past. They simply continued through different sequences of events. In this framework, they are not imaginary possibilities. They are outcomes. Each version experiences its own continuity. Each remembers being the original. Each feels uniquely real from the inside. None possesses a privileged claim to authenticity because the branching process creates no central observer standing above the others. There is only the unfolding wave function. The consequence is subtle but profound. Many of the questions people ask throughout life revolve around roads not taken. What if a different choice had been made? What if a different opportunity had been accepted? What if a different direction had been followed? Ordinarily, those possibilities appear lost. But within many worlds, they are not lost at all. They continue elsewhere, developing beyond your reach. The branches do not communicate. Information cannot pass between them. You cannot compare outcomes or exchange memories. Those other lives remain inaccessible, completely separate. Yet their separation does not make them unreal. In the interpretation's logic, they possess the same ontological status, meaning the same degree of existence as the life you experience now. But there is an important balance to this idea. Multiplicity does not erase individuality. You may not be the only version of yourself within the multiverse, yet you remain the only version experiencing this exact chain of moments. This conversation, this room, this sequence of thoughts, and this particular path through reality belong exclusively to the observer you happen to be. Among all possible branches, your awareness exists here. And here is where your universe becomes real. Before following any idea to its furthest conclusion, science asks a difficult question: where does the evidence end? That question becomes essential here. The concept of quantum immortality emerges from genuine physics. It is built upon established equations, respected interpretations, and decades of serious discussion among physicists and philosophers. But it also occupies territory where certainty becomes difficult to find. The closer we approach the limits of knowledge, the more important intellectual caution becomes. The first limitation concerns the foundation itself. Many worlds remains an interpretation of quantum mechanics, not an experimentally verified fact about reality. The mathematical predictions of quantum mechanics are extraordinarily successful. Laboratories around the world confirm them daily, yet the equations alone do not tell us what reality actually is. Several competing interpretations coexist. The Copenhagen interpretation remains influential. Relational quantum mechanics proposes that physical properties exist only relative to observers. Cubism treats quantum states as descriptions of knowledge rather than objective reality. Pilot wave theory introduces hidden variables guiding particles along definite paths. Each framework reproduces the same experimental results while offering radically different explanations of what those results mean. The data is shared, the interpretations are not. A second challenge concerns personal identity. The problem appears deceptively simple. If branching occurs, what exactly continues? Imagine two future versions of you emerging from a single branching event. Both possess the same memories. Both believe themselves to be the continuation of the earlier person. Both remember every experience that came before the split. Which one is truly you? Philosophers have debated related questions for centuries through variations of the ship of Theseus paradox, the puzzle of whether something remains the same entity after all its components change. Quantum branching transforms that ancient question into something far stranger. Identity may not divide neatly across multiple continuations. The answer remains unsettled. A third concern arises from the extreme consequences explored earlier. Survival alone may not be enough. If increasingly improbable branches preserve awareness under conditions vastly different from ordinary human existence, can those branches still be meaningfully described as your continued life? The issue is philosophical, but it matters. A fourth limitation is methodological. Quantum immortality cannot be tested in the conventional scientific sense. Outside observers always witness ordinary probabilities. They observe ordinary mortality. Any alleged confirmation could only occur from a subjective perspective that cannot be independently verified. This creates a problem. Scientific theories gain strength through falsifiability, meaning there must be a conceivable observation capable of proving them wrong. Quantum immortality sits uncomfortably close to the boundary where that standard becomes difficult to apply. Finally, there is the measure problem. If every branch exists, what determines probability itself? Why should one future matter more than another? Physicists continue debating how probability emerges from a framework containing all outcomes simultaneously. No universally accepted solution exists. None of these objections erase the argument. They define its horizon. The mathematics is real. The debates are real. The unanswered questions are real as well. Honest science requires holding all three truths together at the same time. Consider a different perspective for a moment. Not a laboratory view, not a mathematical one, but a view measured across the full age of cosmic history. Everything we have explored ultimately leads back to a remarkable fact. You exist. That statement sounds ordinary because we live inside it every day. But from the perspective of physics, it is extraordinary. The atoms forming your body began their journey long before planets existed. Most of the hydrogen within you was created during the first few minutes after the Big Bang, roughly 13.8 billion years ago, when the young universe was hot enough to forge its lightest elements. The heavier atoms arrived later. Carbon, oxygen, calcium, phosphorus, iron, and countless others were assembled inside stars. Nuclear fusion transformed simple elements into more complex ones over millions of years. When those stars exhausted their fuel, many died violently, scattering their contents across space. expanding clouds of stellar debris mixed with interstellar gas, becoming the raw material for future generations of stars, planets, oceans, and eventually living things. You carry that history. Every breath contains atoms older than Earth itself. Every cell preserves a chemical legacy written across billions of years of cosmic evolution. The matter composing your body once belonged to ancient stars that vanished long before the sun existed. But matter alone does not capture what makes this story unusual. At some point, arrangements of atoms became capable of awareness. Molecules organized into living systems. Living systems developed nervous systems. Nervous systems became increasingly complex until they could remember, imagine, calculate, and reflect. The universe produced structures capable of asking how the universe works. That transition changes everything. Carl Sagan expressed the idea with remarkable simplicity when he said that we are a way for the cosmos to know itself. The statement is often quoted because it captures something genuine. Through conscious observers, the universe becomes capable of examining its own history and investigating its own laws. No external witness is required. The observers arise from within. Freeman Dyson reflected on a similar idea in 1979. The more deeply he studied the structure of physical law, the more he felt that minds were not alien intrusions into reality. They were compatible outcomes of the universe's architecture. He was not arguing for design or intention. He was observing that the laws of nature permit beings capable of understanding those laws. Within the many worlds framework, this picture expands even further. Every conscious observer becomes a branch within the larger structure of the universal wave function. Countless perspectives emerge from the same underlying reality. Each experiences a different path. Each carries a different story. Yet your experience remains singular. This branch, this lifetime, this precise sequence of moments. The universe has never viewed itself from exactly this perspective before. Even among countless branches, only one follows this exact path. Through your awareness, the cosmos experiences this moment from here, from now, and from nowhere else. After traveling through equations, interpretations, paradoxes, and cosmic timescales, we arrive at something unexpectedly personal. Not an answer, but a perspective. Physics does not tell you what to value. It does not tell you what choices to make tomorrow morning. It does not tell you how to process loss, how to love another person, or how to face uncertainty. Science describes reality. Meaning remains something we construct from within it. Yet the shape of reality matters. The ideas we have explored suggest a universe far richer than everyday intuition allows. Quantum mechanics reveals a world where certainty gives way to probability. Information appears more durable than matter. Consciousness remains deeply mysterious. The boundaries separating observer and observed, self and cosmos, seem less rigid than they first appear. None of these discoveries provide simple comfort, but they do expand the landscape. If the information associated with your existence cannot be fundamentally destroyed, then the story of your physical presence may not end in the way classical intuition once suggested. The atoms disperse, the structures dissolve, the biological processes cease, yet the informational traces remain woven into the evolving quantum state of reality itself. Whether those traces can ever be reconstructed is unknown. Whether they can ever be experienced again is also unknown. The uncertainty remains honest. Within the many worlds framework, another possibility emerges. Every branching event creates futures that continue independently. Choices that appear exclusive from within one branch unfold differently elsewhere. The lives you never lived may exist as actual histories experienced by versions of you sharing the same beginning. But this realization does not diminish the importance of the present. Quite the opposite. You experience only this branch. You inhabit only this sequence of moments. Other possibilities, if they exist, remain inaccessible. The significance of your life comes not from every path that might exist, but from the one unfolding before you now. This is the path you witness. This is the story you shape. If consciousness is what complex information processing feels like from the inside, then every experience becomes part of a remarkable process. Through perception, memory, curiosity, creativity, and reflection, the universe develops increasingly detailed ways of representing itself. Awareness becomes one of nature's most intricate achievements. But none of this erases grief. The absence left by someone you loved remains real. Their voice no longer reaches this branch. Their presence no longer occupies these moments. Physics offers no equation capable of removing that reality. Loss remains loss, and yet the broader picture may invite a different kind of humility. The universe appears stranger than previous generations imagined. It appears deeper, more interconnected, and more subtle. Boundaries that once seemed absolute increasingly look provisional. Questions once dismissed now sit near the frontier of active research. Perhaps that is the most meaningful conclusion available. Not certainty, wonder. A universe capable of producing conscious observers may be far more expansive than any single lifetime can fully comprehend. And within that vastness, your brief experience remains one unique expression of reality, becoming aware of itself, here and now. Set aside the interpretations for a moment. Set aside the debates, the equations, the competing models, and the unresolved mysteries. After everything we have explored, one question remains standing in the quiet. What are you? Not who you are, not what you do. What are you, physically and fundamentally, within the structure of reality itself? From the perspective of modern physics, you are not a fixed object. Every atom in your body is in motion. Every cell is constantly exchanging material with its surroundings. Over the course of years, much of the matter composing you is replaced. Yet, through all of that change, something persists. A pattern remains. The hydrogen atoms within your body were born during the first minutes after the Big Bang, approximately 13.8 billion years ago. The carbon in your cells was forged inside ancient stars. The calcium in your bones and the iron in your blood were created in stellar furnaces and dispersed through cosmic explosions long before Earth existed. The ingredients are ancient. The arrangement is new. For a brief span of cosmic history, those atoms have come together in a configuration capable of memory, imagination, curiosity, and self-reflection. The universe assembled a structure able to ask questions about the universe itself. That structure is you. Quantum mechanics adds another layer to this picture. The theory describes reality through evolving quantum states, mathematical structures containing information about every possible outcome. Across the interpretations we have examined, one principle appears repeatedly. Information occupies a privileged place in the architecture of nature. It is remarkably difficult to erase. The information associated with your existence, your experiences, your interactions, and your place within reality becomes woven into the larger quantum state of the universe. Particles scatter, stars die, galaxies drift apart. Yet the traces of what occurred remain encoded within the unfolding structure of reality. But whether that constitutes immortality depends entirely upon what you believe the word means. If you identify yourself with matter, your atoms will continue long after your biological life ends. If you identify yourself with information, the universe appears reluctant to discard it. If you identify yourself with conscious experience, then the questions become deeper, because consciousness itself remains one of the greatest unsolved problems in science. No consensus exists. Not yet. The deeper we look, the less absolute the boundary between self and cosmos appears. Every breath exchanges atoms with the atmosphere. Every thought depends upon laws forged in the earliest moments of cosmic history. Every observation links observer and observed into a single physical process. Perhaps separation was never the full story. In the end, the question of what happens after death may not be the most fundamental mystery. Beneath it lies a more profound question, one that physics continues to approach from different directions. What is the thing that experiences? The most precise scientific theories humanity has ever created do not provide a final answer. They offer something quieter. They suggest that you are not outside the universe, looking in. You are part of the universe, looking at itself. For this moment, in this branch, through these eyes, and the universe is very, very large.